last time, I introduced you to the Clapeyron equation and how we could use thermodynamics to empower us with geothermal barometry. That was one step in the application of temperature and pressure. But what if we can now add temperature, pressure, and time and extract it all from a rock? And then look at multiple rocks in order to come up with a pathway. So today's lecture is titled PTT pathways. This is kind of one of the main goals of metamorphic petrology. In the textbook, you can find out more about it on 438 to 441, and then from 565 onwards, somewhat sporadically, unfortunately. P, pressure, T, temperature, little t, time. How can we track the evolution of a system? And in fact, we'll go ahead and put this down in our notes, that we are going to combine geothermometry, geothermobarometry, and geochronology, right? What we talked about a little bit earlier in the semester with how we can extract age from a rock in order to tell a full tectonic story. We could call that a tectonic evolutionary story. Now, to do this, I actually want to just go ahead and start off with a case study. I think it is good to do this. We'll put in some pictures this time, and we've never probably heard of this place. It's called the Wop May Origin in northern Canada. You might have never heard of it. It's very important geologically. It's one of the oldest origins on Earth. Why does that matter? Well, because it tells us how long ago plate tectonics was operating. So take a look at this map just to find out where we are in the world. Oh, let's close that. Here we go. Where is the Wop May? Here it is, up in far northwestern Canada. And the story of the Wop May origin is very interesting. In fact, let's go ahead and put this figure in right here too. And maybe you could sketch this, or maybe just put it in your notes, a couple concepts. And what the idea is of the Wop May is that there are these garnets. That's the most important mineral phase. And the garnets are poikioblastic. And I'll even write that down here. Poikioblastic garnets. The composition of the garnets changes from core to rim. And the composition of the remember what poikioblast means? It means a lot of inclusions. So the composition of the inclusions within the garnet also changes, right? In this place, they've shown the plagioclase composition change. And if we looked at the pattern, what do we see here? The cores are more albite rich, and they're more anorthite rich towards the rim. We need to get some of this information here in the notes. So what do we got about the poikioblastic garnets? They include a bunch of different phases, and the most important of them are going to be plage, and then two that I have not mentioned, kyanite and sillimanite. These all have geothermal barometry potential. So if you were drawing a garnet crystal right now, here's what I want you to have. I want you to have a garnet crystal. We're going to kind of show core versus rim, and there are a lot of sillimanite in the interior. There's a lot of kyanite in the rims, and then throughout the whole thing there is plagioclase, but the plagioclase composition changes so that here it's more AN rich in the rims, and in the cores it's more AB rich, right? There's what your notes should be tracking along with. And maybe we could say something like, we could say the garnets are zoned. That must reflect some PT information. And then we could say that the inclusions have a pattern. Inclusions have a pattern. And the pattern that matters to us is that the core has cold thermometry albite, and it has, what does the core have? The core has sillimanite. No. The core has kyanite. Sorry. The rim, let's just double check this. Yeah. The core has kyanite. I did the colors backwards. My bad, people. The rim has hot anorthite plagioclase, and it has sillimanite. And so we also know a couple timing relationships, right? We know that the core had to form first, and the core, so we know the core is old, and we know the rims are young. And so we have a little bit of a PTT pathway that we can put together here. So here is pressure, here is temperature. If we draw in kind of like gently our kyanite, sillimanite, andalusite, kyanite, sillimanite, andalusite, we have a little bit of temperature information. And what we know is that the core with kyanite and colder, there's our core conditions. And this would be an early T. But then the rim records hotter conditions. And so we know we evolved in this direction. Part of the story I didn't tell you is that we can see that the garnet also starts to show some breakdown with a retrograde path. And so later, we actually think it went this way. So there's T2, and here's T3. And so how would we do this? If this is time, and this is pressure and temperature, then we kind of started off at a maybe we should do it just with pressure. We started off at very high pressure, and then we went to low pressure, and then we went to lower pressure. And if we did the same thing with temperature, which I probably should have done in inverse colors because red usually means heat, it didn't in this case. If we did it with temperature, then we would say we were kind of cold, we got hotter, and then we cooled back down again. There is our PTT evolution. Now, this concept is called a PTT loop. And we'll put this as a big capital B in this lecture. We're going to call it PTT loops. And we started to form a loop here, right? It's supposed to be a circle. Here's at the surface of the Earth. You go deeper into the Earth, then you start to exhume towards the Earth's surface. That's a PTT loop. In this case, notice it's clockwise direction. That's a very normal direction. In fact, there's something we should add right here. This returning to the surface is called exhumation. We'll put that word in again later. So with our PTT loops, we're going on a prograde path, and then you reach peak conditions. So here's like just a generic path, PT. Well, there is usually this path that goes up towards higher conditions. We call that our prograde path. We're getting involved in some origin, some convergent boundary. And then you're going to reach some peak metamorphic conditions, and then the tectonism ends, or you're being brought to the Earth's surface, and this is called our retrograde path. This is the path of exhumation. And when we do exhume something, you can do it in two different ways. You can do it tectonically. Imagine you bringing material up to the Earth's surface along a fault, or you can do it via erosion. So what we're going to do, let's first talk about the prograde paths. Prograde paths. There's a couple important things about prograde paths, and that is that the PT conditions are always producing higher grade minerals. So let's say this is the production of higher grade minerals. I can fit that in right there. Nope, there it is. Minerals. And as you go to higher grade minerals, you actually erase what came before. So sometimes the bottom of the prograde path is actually erased. So we tend to erase what came before. So we can get into these situations where we know what happens at peak conditions, and then we see the retrograde path, but all this information about the prograde is gone, just like it was in the Wop May origin. One of the main reaction that's going on along the prograde path. Let's draw this in. So if this is pressure and temperature, and this is water content, well, one of the main prograde reactions is a dewatering. So if this is, let's say that's 5 weight% water, and here is 0 weight% water. As we go along a prograde path up to, let's say, here's 800 C, here is 400, 200, 600. Well, we're going to go, it kind of wiggles, kind of like, something, let's say, like that. But what we have is that lower grade, think about where facies are. Well, we start to break down different minerals at different temperatures and pressure. Zeolites hold the most water, but they disappear at, let's say, 200 Celsius. Same as around for prehnite Pompeii. And then the chlorites start to go away. And then the biotites start to go away. And then the amphibols start to go away. So as the prograde occurs, what we have is dewatering reactions. That is one of the main things that goes on the prograde path. Now let's talk about the retrograde path briefly. So number 2 here is our retrograde path. Here we have erosion or faulting bring rocks back to surface. That means we are decreasing pressure and temperature. But it's kind of interesting how those two things lag along with one another. So let's do another concept here with retrograde. We are going to produce lower grade minerals, but only when possible. Because what ends up happening is that there is sometimes, we'll say, a kinetic limit if no kinetic limit exists. Thermodynamics says we should produce these lower grade minerals, but sometimes those high grade minerals that form during the peak were actually really stable, and the high grade ones don't want to break down. So we'll just say high grade doesn't want to break down. To break down. So there's our two different pathways, and what we see in nature is that they tend to follow either a clockwise path or a slightly different path. Let me show you one more really important concept here about these paths. This is an image figure from the textbook, and what we see are a path showing, so we'll look at this bottom panel first, and I would recommend you draw this in your notes. Take a quick pause and draw this. So here is a clockwise PTT path, where here's our little times, time 1, time 2, time 3, time 4, whatever time, it doesn't really matter. We're going up a prograde path, we're reaching peak pressures, and then we're reaching peak temperatures. And if we follow the geotherm, we might expect peak pressure and peak temperature to be at the same time. And what we're going to say here is that peak pressure does not equal peak temperature in terms of timing. That's a really important concept for PTT loops. Notice, so here now, this PTT loop is graphed sequentially following an evolution with temperature and with pressure. And so here, this line right here, this is the pressure line, and here in blue, this is the temperature line. And notice that what you end up getting is that pressure reacts faster. Temperature has a lag, and that's the main concept here. Temperature has a lag, and the reason for that lag is thermal conductivity. The rocks, when they get to a certain pressure, have to feel the depth immediately. There's no lag with the lithostatic gradient, but they have to heat up, and they heat up slowly, and they heat up much more slowly than pressure, so we get this lag to occur. Lag to occur. So we'll say temperature is a lag caused by the slow thermal conductivity of rock. it heats up slower, and it also cools down slower. So as we're making our way towards the Earth's surface via exhumation or erosion and faulting, the rock actually can heat up even though it's going to shallower conditions because of this thermal lag. So let's talk about the two different types of loops and then end this lecture. So the first type of loop is a Peruvian loop. You remember this word Peruvian? That was a type of zone. And what type of zone was it? It was the type of zone associated with regional metamorphism or orogenesis. Mountain building, right? Regional metamorphism, orogenesis. These are the big genesis. There, it's spelled correctly. The Peruvian loops have clockwise P, T, T paths. So what we see in a Peruvian loop in terms of graphing it, here's pressure, here's temperature, is that we get our prograde path, something like this, and this is our orogeny. Then we're going to reach peak conditions. Here's peak. Now we're going to start exhuming it, but it still heats up because of the thermal lag, and then eventually the exhumation continues and the rock kind of catches up on temperature and we get it to the Earth's surface. Okay, so we have that clockwise. How do we draw a clock? There's our clockwise. It's a clockwise progression. And if what we have then, if we labeled each of these 1, 2, 3, and 4, what we have is, in terms of science speak, isothermal or near isothermal. Isothermal means same temperature. So this is not exactly same temperature. I could have maybe drawn it a little steeper, but it's called isothermal thickening. We're taking it down deeper into the Earth's crust. It's caught in a mountain building event. Then there's a period where you're at very high pressure. It's almost isobaric, but it's warming up as it's caught down in the deep depths of the mountain range. So this part is called isobaric heating. Then we have a time where it's starting to bring itself back up to the surface very quickly. Temperature doesn't have to change very much here. I've just drawn it heating slightly, but it could even be isothermal. In general, in the textbook, it's called isothermal decompression. And then the last step is isothermal or, isobaric or near isobaric cooling. So using the word iso might have not been quite appropriate, but we could say near isobaric, or at least that's not the variable that's changing as much as the other. So we'll put one small note here and we'll say that loop tries to follow geotherm, but thermal conductivity creates a lag. But we'll insert a word right here. Slow thermal conductivity creates a lag. Another way to say that would be that tectonics, erosion are faster than thermal conductivity. They can outpace the temperature equilibration in the rock. Now, the last type of loop we can worry about is called a Buckin loop. Of course, associated with Buckin zones. Remember Buckin zones, they're high temperature changing, but they are very low pressure changing, right? So we can say, recall high T, low P. And the loop, actually, because of this, actually doesn't even really look too much like a loop. We have pressure and we have temperature, and what ends up happening with a Buckin style, as temperature across the region goes up, temperature goes up, and pressure doesn't change much at all. Sometimes there's a little uptick, maybe here at the end, before it returns back to the Earth's surface. So what we'll just say here is that little pressure change, maybe a small increase at the end, and the reason for it is probably like, here's our system, and let's say there's a lot of magmas intruding into the crust. Well, they have to make space for themselves, and so as they make space for themselves, they're pressurizing the whole area, right? Because they're adding volume to a set area. So we could say that maybe small increase in P attributed to intrusions shouldering their way through. And then to wrap it up, I'm going to throw in an image. This is from a publication looking at a place in the world in Italy called the Doramira. The Doramira is this really incredibly scenic place in northern Italy in the Alps, where there's been fantastic science done on how fast those rocks went from the core of the Alps. All right, so they used to be here. The Doramira used to be the core of the Alps, and then because of faulting, they ended up getting exposed at the surface of the Alps. How would we draw that? We could draw it like put a reverse thrust fault in, and so now that thrust fault has brought those rocks up to the surface of the Alps from depth. How fast and how deep? Well, if you look at some of the cores of minerals, they tell you that we get at 35 million years ago, we were at, how deep is that? 110 and 800 C. And then at 33 million years ago, well, the rocks were only at 40 kilometers depth. And then at 32 million years ago, they're at 20 kilometers depth. And that's a really powerful thing, because if you know, what do we know? We know age and we know depth. Well, then what we can do is we can calculate an excimation rate. How fast are the faults moving? And that's what's being plotted here. So to go from this depth to this depth in only 2 million years, well, that requires an incredibly fast excimation rate. That's an exciting area of metamorphic petrology applied to tectonics.